everybody and welcome back to my channel. So today we are going to learn about heaps. Now heap is a data structure, but unlike other data structures such as arrays, stacks or queues, the values inside the heap are not in any random order but are managed meaningfully by the heap itself. Now let's first see how a heap looks like. A heap is an almost complete binary tree. Now any binary tree is said to be almost complete binary tree when it obeys two rules. The first rule is that every level will be filled once the last level is completely filled. And the next rule is that first we are going to add the left node. First the left node is added and then the right node is added. Now in order to understand these two rules clearly, let me show you some examples. Now if suppose I have a binary tree like this. Now over here we can see that first these two levels are completely filled and then this last level has a node. That means after filling these two levels completely, we are adding the nodes in the last level. So the first rule is valid over here. Now in the second rule over here we can see that if there is a right node, then it must have its corresponding left node, which means that a right node can be added only when a left node is already added over there. Now over here we can see first the left node is added. Now if instead of this, if my tree looked like this, so this is not an almost complete binary tree because over here we have a right node to a parent who doesn't have a left node. So this is not an almost complete binary tree. But now this becomes an almost complete binary tree. Also, if in my binary tree I had a node over here, this is still not a binary tree because first the children of these are to be added and only then we can add the children to this node. So some other examples of almost complete binary tree can be like these. So these are some examples of complete binary tree. Now this is the way we imagine a heap looks like, but internally heap is nothing but an array. So if I have a heap which looks like this, 10, 12, 14, 15 and 16. Now if I have a heap like this, so internally it will be stored as a sequence of numbers, and in the array we are going to store all the numbers level by level. So first we are going to have 10, then we'll have 12, then we'll have 14, then 15 and then 16. Now let's see how we can see that which is the parent and which are the child nodes to that parent. Now over here we can see that 10 has two children nodes, 12 and 14. So 10 has these two children nodes. 12 has two children nodes, 15 and 16. So these are the two children nodes to 12. Now if suppose I had 17 over here, so 17 will be here and 14 has the child node 17. Now in order to see that which children belongs to which parents, let's analyze the indexes of these elements. Now these are the indexes where we have stored the number. Over here we can see that if 0 is the parent, the children of 0 are at index 1 and 2. And if 1 is the parent, the children are at index 3 and 4. Also if 2 is the parent, the children are at 5. Over here it is at 5. Also if we had another child as 18, so it will be here and its child will be at 6. So it will be at 5 and 6. Now if I had 2 more children over here, so these 2 will come over here at 7 and 8 and they are the children of 15. So for the third index, the children are at 7 and 8. Now using these values, what we can tell is that if my parent is at index I, then the children will be at index 2 into I plus 1 and 2 into I plus 2. See, over here it is 0. So 2 into 0 plus 1 is 1 and 2 into 0 plus 2 is 2. And over here we can see that I is 1. So 2 into 1 plus 1 is 3 and 2 into 1 plus 2 is 4. So this is how we access the parents and children in the array. So a heap is this heap is just our imagination in order to analyze better how a heap works, but internally a heap is nothing but an array. Now there are two types of heaps. One is the min heap and the other is the max heap. Now as the name suggests, in a min heap, the parent node will have smaller value than its two children nodes. So if this has 8, so these two must have values greater than 8. Now they can be anything, but it has to be greater than 8. Now in a max heap, the parent node should have a value greater than its two children. So over here we have suppose 9. So over here we'll have numbers less than 9. Now there is a relationship between the parent and child, but there is no relationship between the two siblings, which is two children of the parent node. Now let's see some of the properties of heap. Now over here we can see that this is a min heap because the parent node has a smaller value than the two children nodes. Similarly, over here the parent node has smaller value than the children nodes, and similarly over here. So from here we can say that this whole is a heap, a min heap, if the sub heaps are also min heap. Now if over here I had 70, then these three are fulfilling the condition of min heap, but this won't fulfill the condition of min heap. So almost complete binary tree is said to be a min heap if all the sub binary trees are also min heap. So now let's see how we can add or remove any number from a min heap. Now if I want to add any number to this, so what I am going to do is I am going to add that number to the end. Now if suppose I had to add 8, so technically the 8 should be the root of the tree because it is the smallest number, but it is really difficult to add the node directly at its correct position. So what we do is we go to the last, we go to the place where the next element will come. So I'll just add the node at the last. and now I am going to traverse upwards, which means that I'll check if my parent is greater than my node, this current node. Then we are going to swap the numbers. Now as 13 is greater than 8, we are going to swap 8 and 13. Now I am going to again check if 8 is in the correct position, and 8 can be in the correct position only when its value is greater than the parent node's value and its value is smaller than its both children node. So the children node are taken care of. Now we are going to check these two numbers. Now since my parent node has a greater value, we are again going to swap the number. So over here we'll have 8 and over here we'll have 11. So now our heap looks like this. We have 8, 12, 11, 15 and 70, 80 and 13. So this is still a min heap. Now if we have to add another number, so we are going to add it over here, and we are going to traverse to the top in order to see, in order to place my element in the correct position. Now if suppose I had to add 10 over here, so I'll place 10 over here, and now I'm going to see. Now 10 is smaller than 15, so we are going to swap these two. Over here we'll have 15 and over here we'll have 10. Now 10 is again smaller than its parent, so we are going to swap these two. Now over here we can say that 10 is greater than the parent. So this means that 10 has come at its correct position and no more swaps are to be made. Now this operation of checking of parent and swapping the numbers if they are in not correct order is known as heapify in the upwards direction. As we are going from the last level to towards the top level, which is towards our root, this is known as heapify in upward direction. Now over here we can see a very important property, which is that the root of the min heap will have the smallest element amongst the tree. So if I talk about this min heap, so 8 is the smallest element. Now if I talk about this part of the tree, which is also a min heap, 12 is the smallest element amongst all these nodes, and in this part 11 is the smallest number amongst these nodes. Now if I want to have the smallest number, or if I want to delete the smallest number from a min heap, I have to delete the root node. Now let's see how we can delete a root node. We know that if any nodes get deleted from our heap, the last node will not be over here, because as it is a almost complete binary tree, all these levels and these all nodes will be added first, and then there will be a node over here. So we have to do something as such that this area gets vacant and we take this element and put it in its correct position. Now as 8 has to be deleted, we'll remove 13 and we'll just put 13 over here. Now see, 8 is no longer in the heap, but this is not a min heap right now, as 13 is in the wrong position. So now what we are going to do is, we are going to traverse downwards and put this 13 in its correct position. Now let's see how we do this. Now over here we can see that 13 is greater than these two elements, which are its children nodes, and we know that this should have a value which is greater than both its children nodes. So we are going to have the minimum value between the two children nodes. So over here the minimum value is 11, and hence we will have 11 as our parent node. So I just swap these two elements. Now we cannot put 12 over here, because if we had put 12 over here, so it would look like this. And 12 cannot come over here, as 12 is greater than 11. And this should be smaller than both its children nodes. Now we are going to check again if 13 is in the correct position. We check that 80 is greater than 13. So this means that it is satisfying the property of min heap. Now if over here I had another value as 11, so over here we see that this is not a min heap, as 11 is smaller than 13. So we are going to swap these two elements. And now we can see that our min heap is again retained. So the heap now looks like this. So what you have to remember is, if you have to add any node to the heap, just add it at the last index and then perform the heapify in the upwards direction, which means that we are going to place the last elements in its correct position. And if we have to delete any element from the heap, just replace that element with the element at the last index and perform heapify in downwards direction, so that that element which has been placed instead of the element which has to be deleted gets in its correct position. So now let's see how much time does a heap takes in order to maintain the elements in a proper order. Now the functions that we use are, first is the add function, second is the delete function, third is the heapify up function, fourth is the heapify down function. Now let's analyze their time complexity. Now we know that in the add function, we just simply add the node at the last index, which takes time of order of 1, and then we simply call heapify up. So the time complexity of add will be that of heapify up. Now in the delete, we simply replace the last element and the target node which has to be deleted, which takes order of 1, and then we just call heapify down. So the time complexity of delete function will be same as the time complexity of the heapify down function. Now let's see how much time these two heapify functions take. Now as we know that in heapify up, we move from the root node, from the leaf node to the root node, and in heapify down, we move from the root node to the leaf node. So we clearly know that the time complexity for heapify up and heapify down will be the total height of the tree, because no other element or no other node is being traversed, only the path from the leaf to root is being taken care of. So now as we know that heap is an almost complete binary tree. Now an almost complete binary tree is always balanced, and we know that for a balanced tree the height is always log n, where n are the total number of nodes, and this is of base 2, and we have base 2 because every node has at max 2 children. So the height of the tree will be log n, and the heapify up and heapify down will take the time of the height of the tree. So these both functions work in order of log n. So our add and delete function takes order of log n time. Now we know that whenever we are creating a heap, so we are adding all our elements to the heap. So for n elements, we perform our add function. So technically it should take n into log n time. But there is a very better method which takes order of n time. Now let's see how we can build a heap in order of n time. Now let us take an array. Now suppose we have this array. Now if instead of adding every element one by one, let's just create a heap of these elements only. Now it is not necessarily a min heap or max heap. We'll just create a heap out of it. So our heap will look like this. Now we know that a single node is always following the property of min heap or max heap, because there are no children to compare with. So we know that a single node is always a min heap or max heap. So we can assume that these nodes are already in the correct position. They are not in the correct position, but initially we assume that these nodes are in the correct position. So first we'll place this node in the correct position, as we are certain that these nodes might not be in their correct position. So over here, as we know that we have assumed that these nodes are in the correct position, so over here 15 will ask the children that am I smaller than you both in case of min heap, and it will ask the children am I greater than both of you in the case of max heap. Now if this is true, then we'll assume that this is in the correct place, and then we'll go over here. So over here, let's do it for a min heap. Over here we'll see that 14 asks both the children, am I smaller than both of you? So it says yes. Then we go to 11. Now 11 also asks that am I smaller than both of you? So it says yes. And then we go to 12. Now when we go to 12, it asks its children that am I smaller than both of you? So we get a no from the right child, because right child is 11. So we simply swap the two elements. And now if in case both the children are smaller than this node, so we are going to swap it with the minimum value. Now after this node is in the correct position, we'll go up. Over here we'll see where this will ask both its children, am I smaller? It says yes. Now if in case this number was 70, so let's see what happens. Now over here, if number is 70, then it knows that it is greater than its children node, and where it should have been smaller. So it is going to pick the smaller number. Now over here, since both are same, let's take any of them. Let's take this number. So we are going to swap these two. As this node is currently altered, so it will have to verify if it is in the correct position. So 70 is again going to ask its children that am I smaller than both of you? So it receives the answer no. So over here the smaller one is 12. So over here we'll have 70, and over here we'll have 12. Now we'll do this operation unless and until we find the correct position or we reach at the leaf node, as the leaf node is always a correct position for any node. So once we reach the leaf node or we reach the correct place, we stop. So over here we are applying the down heapify method in order to place my number in the correct position. And also we are not applying the down heapify function for all of the nodes, but for only n by 2 nodes. As we know that when we have n nodes in an almost complete binary tree, we will have n by 2 nodes as the internal nodes, which means that they have at least one child, and n by 2 nodes will be our leaf nodes, which means that they won't have any child. So we will be applying the down heapify method only on n by 2 elements. Now you can also assume that if we are applying down heapify method on n by 2 elements, so the complexity should have been n by 2 log n, which is again of order of n log n. But this is not the scenario, as when we calculate its time complexity in detail, so we get a decreasing GP series, and because of that decreasing GP series, the time complexity comes out to be order of n. So this is a way using which we can build a heap in order of n. So over here we have now a new function named as build heap, which takes order of n. So this was all for today's video. Tomorrow I will be implementing heap, and day after tomorrow I will be uploading a video related to heap sort. So the heap that we are going to implement tomorrow will be used in that heap sort. Also, if you have any doubts, you can leave a comment down below, and if you want me to solve any particular question of yours, leave it in the comment section with hashtag #CodeMyQuestion. If you like my videos, please subscribe to my channel. Also, if you find it useful, then please spread it across. Thank you.